A lot of interesting stuff happens in the hallway. It happens, you get to walk out of a session and there's a collective experience that you just went through. And so there will be a hallway conversation that springs up discussing the material.
Well, welcome to a session that I did not know I was going to give until I foolishly volunteered about a week ago. I've actually not given a talk about contracts. I've mentioned it in a couple of slides. I've not given a talk about contracts. I am a Johnny-come-lately. There are lots of people in this room who know much more about this than I do, so I'm going to do my best, and the errors are mine. But I would also like to acknowledge that this has been going on since the run-up to C++20 to 0, not 6. So because we have folks in the room, if you have ever written a paper or written a line of code of implementation or participated in reflector discussions or been in EWG or SG21 discussions, if you have contributed in any way to contract, would you just please stand up right now? Can we give them a hand, please? All the folks. These are just a subset of the folks who've worked hard on this. So the current status of contracts is that they are in draft C++26. The committee experts had consensus to do that in February. There remain questions about it. We have 2 more meetings of technical fit and finish before C++26 is actually cast in stone. And we're going to talk about contracts again in November at our next meeting, including whether to fix it or whether to delay. So what's in there now is what I'm going to describe, but every concern will continue to get a full hearing. I just want to represent the status of it correctly. And this talk summarizes my best understanding, but I can be wrong and often am. By the way, being wrong is good because you learn as long as you welcome being wrong. And so you should treat all the answers in here also as provisional, depending on changes that might yet happen. But let me describe what I know from talking to folks who have concerns and also who've worked hard on this feature. And I'm going to start by making myself a target, because a lot of people are interested in contracts, but there are 2 groups with very strong opinions about it. There are many experts who strongly believe that C++26 contracts are beautiful and ready to go. And there are others who think they're not ready and shouldn't ship yet. How many of you think that I can offend both of those groups in 2 sentences? Come on, a little more faith. C++26 contracts have open questions and do not yet have widespread deployment experience. Just offended some people. We likely will not get a substantially better design than C++26 contracts without wishing for magic linker improvements. I have now offended other people. Let's go. We're going to talk about motivation. Why does virtually everyone agree that some contracts in some form is a great idea? Then we're going to talk about what's there today, best practices that we're starting to learn and explore, some rationale, and some frequently asked questions. But let's start with safety. Because yes, contracts are about safety, but they're not about type and memory safety. The bottom of the slide, type and memory safety are about guarantees that you can give in the language, like that every null pointer dereference gets trapped. If we ever have a rule like that, that's a language guarantee that a certain category of memory safety error cannot happen. You didn't have to write special code. It's just a guarantee you get. And that includes guarantees by static analysis tools if you refuse check-in if your code doesn't pass static analysis, right? So it's build time rules give guarantees. That's the bottom half of the slide. Contracts are the top half of the slide. They're about functional safety. They're not about directly about did I do a buffer overflow. They're about does my system meet its requirements? Does my car accelerate and especially stop when it's supposed to? Does my medical device operate on a pacemaker? Does it keep rhythm? Does it respond in time, in real-time messages? Things like that, that we want to use assertions for. And there we basically get a knob we can turn, because the more assertions we write, the more coverage we get in our code. But that's not a guarantee, right? It's a work harder, get more effort, whether it's an assertion you wrote or in a library you wrote, right? It's a dial. And so functional safety is not the same as memory safety. Where the overlap could come in is if in the future, if we continue to have C++26 contracts, if we in the future make language guarantees, like we actually did a bit for the hardened standard library, that are expressed in terms of a contract check. So if null pointer dereference is a contract check, the contract assert not null, there's the overlap, but you get the memory safety not because it's a contract, that's an implementation detail. It's because the language feature happens to use the contracts feature. It's a uses a relationship, right? So just tease those apart. For the rest of this talk, I'm not going to talk about the safeties, but that's just to demarcate the line. You're doing code review. You see this function. What could be better? What comment might you make? Just shout it out. Take a reference. Okay, let's say you're going to take a pointer. What else can we say about the body of the function? Check for null. Thank you, Oleg. Someone I recognize. So yeah, you'll notice that there is an unconditional dereference here of the pointer. And so immediately you can see into the mind of the author of this code, and you know one of two things is true. They either knew that, and they think they know because all possible code paths that could flow to this function, and structurally it could never be null, so they don't check it, or they forgot. We've been both of these, right? How do you know reading this code? You don't. If you write one more line, now you do. You've expressed your intent. If you've ever seen one of my talks, you are going to get tired of me saying, we want people to express their intent directly. We do that. Now, not only does the code reader, who's going to read the code, which could be us a year from now, understand the assumption that's being made, but tools can check it for us, even for lowly C assert. Now, we've had this advice for a long time. When Andre and I wrote the book C++ Coding Standards, we collaborated a lot. So we each wrote different items and then edited them together. Andre wrote this one. Andre, are you in the room? Wave if you are. No. Oh yeah, there he is. All right, Andre. Thank you for writing this, because I knew about C assert before you told me about it. Like, I've known about it since the 80s, right? One of the things we learned. I did not realize how important it was to systematically use it because no one taught me. And I never worked in a shop where that was the culture. We can all have blind spots. And the assertion, I've highlighted a few things, it must always be true, and otherwise it's a programming error, so it's about programming bugs. Never write expressions with side effects, we'll talk about that. But let me read the bottom quote. And I want you to see how useful this quote, because I'm pretty sure you wrote this text, Andre, because it's written in a kind of professorial voice. It's not a bad thing. It's just a different thing. Because when you get assert religion and you start telling other people, hey, you should write asserts more, whether it's assert or your homebrew version or contracts or something else, one of the pieces of resistance that you will encounter is you will encounter people who say, look, I've been programming X years, I use them here and there, but you're wasting my time if you are telling me to write the assertion here in this my favorite function that I know very well, because I know that this assertion that you were telling me I should write could never fail. Like that is a stupid assertion to write because it's not something that could ever fail. Okay, you are going to hear this. Andre's response, I will not, or Romanian accent. According to information theory, the quantity of information in an event is inversely proportional to the likelihood of that event happening. Thus, the less likely some assert is to fire, the more information it will bring you when it fires. So, do you see the judo move? The judo move is that person who just told you Why? This is the assertion of all assertions that is stupid to write because it will never fire. They just gave an ironclad reason why that is the one they absolutely should write. Because if it ever does fire, it is the most valuable assertion they will have ever written. Also, that smart person may even be right that assertion will never fire today. If the code is successful, it will get maintained. We know what happens when we write code, including in maintenance. When we write code, we write bugs. Always true. So I have never until this one time actually sent a YouTube video to the C++ committee. I actually sent a YouTube short to the committee because I thought it was important to see your customer, to understand the value the community sees in assertions. In this particular video, I just happened to be going through YouTube Shorts one day, as one does, and this example came up, and this is not even in C++. The programmer is writing TypeScript. They're using Node.js assertions. And notice that this video got 4 million, just about 4 million views as of right now. And I want you to see this video for yourself. So let's just go and listen to our customer.
In my program,
Let me start it at the beginning.
I just changed the way I program after doing it for 20 years. It's called negative space programming. Let's take this function right here called morphFoo. It expects foo.bar to be a number. At this point in my program, I know that foo.bar is actually a number, despite its definition saying, hey, bar might not be a number. Therefore, I'm going to assert that this behavior exists. I am effectively programming in the invariance in my program to guarantee behavior. And when my program crashes, then I know either that I was wrong about my worldview, or 2, I have a bug that demands fixing. I cannot tell you how much better this has made my life and the quality of the programs I build. I just changed the way I program after doing it for 20 years.
That is a delighted customer. That is what we want to do, we hope, with contracts. We can make a mistake here, though. It would be very easy to say, oh, I don't know who that is. Maybe it's some jock programmer who's self-taught and is now a YouTube influencer, and oh, maybe I don't even want to see the code he writes. And after 20 years, come on, I'm a CS grad, and 20 years, he should know better. I just told you it took me 20 years because nobody taught me. I am him. I didn't know to use asserts systematically until well into the middle of my career. So let's see the delighted customer, but let's all welcome someone learning. This is a good thing. So we talked about motivation, why defensive programming. Now let's see what is in the current design of C++26. It's pretty much summarized. This mic keeps cutting out. I don't know if you might have an alternate, but we'll try to keep going. I asked a certain AI, and maybe I'll just use a handheld if you have got one. Give an example C++ function that should use assert in 3 different ways. Now the reason I did this is because I decided that I was about to write an example myself, but then testing, great. I was about to write an example myself, and then I thought, well, maybe I can accelerate this. So I asked ChatGPT to do this, and here is what ChatGPT came up with. Anyone spot the bug? This won't compile. This is make fun of our favorite AI day. Going once? Going twice? Shout it out if you see it. There's no declaration for sum. Good try though, ChatGPT. In the top right, you'll see that I actually did a second prompt as well. That prompt was, show me the ChatGPT logo with amusing little red devil horns. And it did a pretty good job. So I said, well, this is a good start, but let me fix this function. Can we just take the level a little down? Fix this function, and here is what a similar function would look like in C++26 contracts. So we see we can move some of the assertions out of the body of the function into the interface. So the precondition we can now state up front, One of the benefits of that is it's visible to callers. It's on the declaration. Not just human callers, but also static analysis tools will have a much easier time with this. There's a talk about this later in the week. The post condition, where if the post condition is wrong, it's a bug in this function, is now also stated in its declaration. And then we have a contract assert in the body of the function, and what that is doing is essentially checking a precondition, it turns out in this case, because it's checking input, but it's doing it while processing the input so we don't have the overhead of a second path. So that just gives you a flavor for the kinds of things that can be done with contracts. Preconditions, postconditions, and contract assert. Why is it not spelled assert? Macros. There are 4 ways to treat contracts. They're called semantics. Ignore, observe, enforce, and quick enforce. And here's what they do in one slide. You will notice that they not coincidentally handle exactly every combination of the right 2 columns. We initially had just the first 3, and then Apple pointed out we need number 4, and so we added number 4, quick enforce. One of the nice things is that for the first combination of the 2 columns, where we don't call a violation handler and we don't terminate, we also don't even evaluate the predicate. So there's 0 cost if we are in ignore mode. 2 of these might be familiar because ignore and enforce are what we're used to with, say, assert. Finally, we also have a way to handle a contract violation. This is a global function that you can write. You replace it just like you do a new handler. And what that lets you do is if there is a contract violation, and if you're in one of those modes that call the violation handler, observe or enforce, then you can get information about it, including typically the source location, the quality of implementation guidances for preconditions to give the source line of the caller of the function, which is useful because the bug is in them if they fail to meet the precondition. The comment, which could be a pretty printed version of the predicate, and other similar information. Like all global replacement functions, it's provided at link time. So you write it once for the whole program. You don't get to change it at runtime. There would be security issues there. By the way, you'll notice that the icon I use for this is intended to be ecumenical. It is both the UK and the US. Since the UK-US schism back in, was it 10,000? No, that was a different schism. We have had different ways of calling emergency numbers. 999 is the oldest. In 1937, London got the 999 code, which at the time, I'm showing a push-button phone, but that's an anachronism. It's because if you were in a fire and you couldn't see, it was dark or there was smoke, you could, with a rotary phone, easily tell which was the number adjacent to the stop. And you could find that by touch in a smoke-filled room. And so yes, 9 was longer. Why not just do 111? Because it's easier to find 9 when you're blind or blind dead. And so that's important. The US version is the bat signal. That's what we use everywhere else throughout the United States here today. By the way, I say don't be Thomas Duffy because mere days after 999 was instituted, Thomas Duffy was reported and arrested for burglary. So it started working right away. So as soon as you start providing a way to report violations, good reports come in. So we talked about pre-post contract assert and handle contract violation and the 4 semantics. Now here's where we would love a Scott Myers to come and write effective C++ contracts. So good news and bad news. The bad news is, well, he's retired, and I actually tried to get him to this conference, and he just wouldn't take the bait. He's still very much retired. The good news is we're going to learn more, of course, but so far I only know a handful. So it's actually going to be a very short book at the moment. Here's what I know so far. Before I get to item 0, because we start at 0, let's please crisply distinguish between program bugs and runtime errors. And I use the example of vector subscripting. I subscript a vector index index, the indexed element. Is that a bug or a user error? Well, it depends who's responsible for the value of index, right? If index is something that you computed in your program, in code, and it's out of bounds, I am very sorry, you have a bug, go fix your bug. Like the user could not do anything. You gave them a broken program. So go fix the bug. Contract assert is, or a precondition or a postcondition is the right tool for that job. Reporting an error to the caller, like just returning an error code from the function, for example, or throwing an exception usually, although we'll talk about exceptions in a moment, for normal error reporting is just not really appropriate because by definition the program is in a state that you never expected it to be in when you wrote the program. It's in a state it wasn't expected to handle. If that index is wrong, it is likely other things are already wrong too. Having said that, there is sometimes some recovery we can do. However, on the right-hand side, if index is read from user input, they typed in the index on the console, or you read it from a data file or on a network stream, and it's out of bounds, user, go fix your data, go fix your input. That's a runtime error, and we want to check that with an if, and then with error handling logic. So the bottom line, assertions are not for runtime input validation. And now we can generalize this a little bit. So item 0, and these are all drafts, I reserve the right to improve these or decide I was wrong, but this is the first draft of this item for me. Never use contracts or assertions for program logic. One example is using contracts for runtime input validation. It's not what it's for. Another is to use contracts for normal program behavior, to rely on things like side effects. Not what it's for. And I love this quote by Lisa Lippincott, and thank you, Timur, for showing this to me mere hours ago, from a talk that she gave here at CppCon last year, so I appreciate the reminder. Lisa says, the first thing to know about assertions is they are redundant. If you're writing something that's not redundant, don't use an assertion. This is a basic fact of information theory. There is no error, and here we're talking about program bugs, not runtime errors. There is no error detection without redundancy. That's what CRC is for. That's what sharding and duplication is for in a resilient database, right? You want error detection, it means you want redundancy. It's inherently the case. So item 1 is actually a corollary of item 0, or a corollary, depending where you're from. Don't do side effects in a contract check. And this is true of any contract anywhere. It can be assert, it could be C++26 contracts, it could be in other mechanisms in other languages. In assert, why not? Well, because the predicate might be evaluated or not, might execute or not. In C++26 contracts, the answer is because it might execute 0 or more times. It might execute not or multiple times, depending. So the good news, and this is a little controversial, but even if you're in the camp that thinks this is controversial, I think you will agree in this example on this slide, it is good that this is actually a compile time error. The reason it's a compile time error is because one of the things that was fiercely debated about contracts was that they implicitly, when you refer to a variable, it is implicitly const, specifically to make it harder to write side effects. Trust me, you can still write side effects. We know you C++ programmers. We know how to do things, right? Even without constcast. But many things can be caught, including this one. And this will be a compile time error, which is way better than assert. Number 2, avoid splitting compound conditions. To me, this actually comes down to a much simpler thing. It's not always applicable, but it is in many of the examples I've seen. If you want short circuit evaluation, you have to type $ampersand. That's true all over the language. We have lots of cases where people have said, oh, I didn't get short circuit evaluation, but they didn't write $ampersand. I mean, that's just how it is. You need the built-in and to get, or to get short circuit evaluation. So if you have the first contract condition, P is not null, and dereference P, you're guaranteed to never dereference the P because of short circuit evaluation. If P is null, you'll never get to the second part of the predicate. Yay. If you split them up, as in the bad example, And you're running with the observe semantic, which means we check the predicate, we call the violation handler if it's false, but then we continue. We don't terminate, we continue. We're just observing. Then it's possible that you will get undefined behavior in the second one, the second predicate check, if P was null. But even in observe mode, the first check will still get checked. Your violation handler will get called. So when your program crashes, you will have the information with the smoking gun saying, you violated effective contracts item 2. It might even say something like that. If not, you'll remember this example from this talk, hopefully. It'll tell you what you did wrong. Item 3 is, does it make sense to use a violation handler that throws an exception? Can that be reasonable? So the first case where it's reasonable is not a normal use of contracts. It's not you're checking things about your program. It's that you're testing the contracts themselves. You're in a test harness where contracts are code, so you may want to test them. I generally don't do this, but many good hygiene shops do this. They say, I want to make sure that my assertions fire when they're supposed to if I made a mistake. And so they test them. If you test them by deliberately violating the assertion, and then you terminate your program, and then you spin up a new program, and you go to the second assertion and try that one and do negative testing, there could be overhead and just restarting. You're getting basically one assertion checked per execution. If you throw and assume you do the cleanup so that you're not actually in a corrupt state, wink, wink, then you can go and do and test more of these with an exception for each one without loading the executable this n number of times. So that's the idea. It's to optimize testing the contracts themselves. But now let's go back to regular uses of contracts. There are legitimately cases where it is not acceptable to terminate. And I generally find, this isn't always true, but I very frequently find when I talk to people in this situation, whether they're developers of autonomous space vehicles or autonomous land vehicles, whether they're operating system developers, they want either an exception or terminate because if they want terminate, they want it for a subsystem they can restart. If you're in a whole C++ program and you terminate, the whole program goes away. If you throw an exception, then you can use normal stack unwind to do some cleanup. You're in a corrupt state. Like let's be clear. That subcomponent has failed. It's not that the tire is underinflated. The tire blew. And you're trying now to go back, take off the tire, put on a new one, restart the subcomponent. So that's the idea. I'm seeing nods in the audience. Some of you do this, but for part of your program. That's a perfectly cromulent way, pardon the Simpsons reference, to do a throwing exception violation handler. But beware, and by the way, there's prior art for this, as I note in the bottom. What was, Josh, you're here somewhere, aren't you? Oh, no, he isn't here, okay. Josh Byrne, who did a lot of the work here, he recently sent me a quote. I think the exact words were, you can't swing a rat without hitting a dozen languages that throw exceptions for contract violations. I mean, they all do it. And Bjarne, thank you for telling me at the very same point. Ada, Eiffel, Java, like everybody does this. But as we often remember, C++ is not like other languages necessarily. All languages are different. Just because language A does something doesn't mean language B does something. Now, in this case, it's pretty close. But there is a wrinkle for C++. If you're throwing an exception so that you don't terminate, anybody spot the flaw or the potential flaw? Steve?
You must not throw another exception.
Yeah, there better not be another exception already active. You better not be unwinding. You better be not in a no-throw function that doesn't have a try-catch protecting it because it never thought an exception would happen, but somebody inserted a contract underneath, right? So one way you can mitigate this, especially for the stack unwinding case, and I am saying on the slides, this is totally experimental. I have not tried this. I wrote this on the slides by hand. I don't even know if the code compiled because I didn't try. I know the triple slash doesn't compile. If you're going to install a throwing violation handler, it seems like a good idea, but take this as provisional advice that we're still learning, to at least test the not uncaught exception, that you're not currently unwinding. Because if the whole point was you didn't want to terminate, you probably don't want to throw an exception then. Because you might, depending on which part of unwinding you're in. Item 4, understand how build modes combine. So some of what I'm going to say now is going to reflect that I've spent a large part of my life in Windows land. And can reflect that either A, I don't understand Windows land as well as I think, or I am making generalizations that are not true in Linux land and other nicer environments. So take this with a grain of salt. It is well known in at least some environments you don't link debug and release builds. They may actually link to completely different runtime libraries with different names, different SOs, different DLLs. ndebug is not that, but it's often part of that. ndebug is often set in conjunction with those build modes and those flags. In the Microsoft compiler, it's often set in conjunction with _debug, which absolutely the heck affects ABI because it does iterator debugging and adds extra information. So we already tell people, hey, build everything in the same mode. Do not link debug build code with release build code, at least in some ways. Look, there are a million switches. Many of them are compatible, right? But here are 2 big buckets that we generally know about. And that will give you no ODR violations. But sometimes we can tolerate benign ODR violations. We can, if we're otherwise in the same build mode, say we're building in release mode, and some of our files have ndebug turned on and some don't. That generally still works. Because even though it's technically an ODR violation, the same function may be compiled with debug and without debug. And if it makes it all the way to the linker and the linker sees 2 copies, it may flip a coin or equivalent, flip a bit and decide which one it's going to take. So you have to know those things today. I hope I'm not saying anything new. This is the world we live in because we are in a multi-translation unit. ODR is not strictly enforced. And the linker will help you if it can, world. That is our world. Contracts offer an improvement while staying in this world. One of the design questions was, should we require better linkers? The answer currently is no. The pitfall of saying yes is now we'd be standardizing a feature that relies on tools that don't exist. And what's the danger of relying on tools that don't exist, where you're not just making a language change, but you say, and the tools have to be updated before you can use it? I could name other features we did that with, but the key thing is, then you'd be delaying adoption by at least a decade for those tools to be reliably available, because it's not good enough if they're available on one platform, because so many of us write portable code. And having it available on one platform, great, that's a great start. Call me when you've got it on all the 5 platforms I need. Then I can consider adopting it. And that's the reason why we don't rely on new linkers. The current GCC and Clang contracts implementations, which have not been upstreamed, but one of which might start upstreaming in the next couple of weeks, fingers crossed, do allow linking translation units built with any configuration. The standard does not require that be possible. The standard allows platforms to put restrictions in, but the 2 implementations currently underway do let you mix and match those modes. And I'll show you that can lead to what could be viewed as pitfalls, so I'm going to talk about that later. Well, actually here is now we're at later. Here's the example. This is a brand new paper that just became available in the last couple of weeks, I think it was. It was this month. Imagine you have a header with an inline function that contains a contract assert. And as I describe this, think of, hey, how similar or different this is from a regular assert. F does a contract assert that its parameter is positive, it's greater than 0. Now I have 2 translation units that use it. So let me point to those. There we are. We have the first translation unit on the left. It's built with quick enforce. Now it has a function named G, which calls F out of contract. That should fail because 0 is not greater than 0, so that's a failure. And it should terminate right away without calling a violation handler because it's built with quick enforce. So far, so good. I have a second translation unit, which also calls F, and it's in contract, and that is expected to pass. If the whole program has 2 copies of F, well, the linker will just pick one. And so an issue we have here is if the call on the left-hand side was inlined, then it will be governed by the quick enforce. If it was not inlined, then you're at the mercy of the linker. My understanding, and I could be wrong, is that you can guarantee that local semantic per translation unit. You can guarantee on the left-hand side you will get that quick enforce, but you have to force inline. This is not this is much more easily said than done. You have to force inline. Remember, inline functions includes every template you ever wrote, because they're all inline in headers, because C++. But if you can arrange to make sure that they contract assert is in the body of the CPP file, it actually makes it to the body and is compiled, then you're good. Then you know the quick enforce will happen. And the benefit is that not only do you get that, so you get what you want on the left, but the author of main.cpp gets what they want. They get guaranteed ignore with 0 runtime cost. And this is actually will link without an ODR violation, which is a huge improvement over assert. I should say it will link in current implementations that are now close to being upstreamed or being proposed for upstream in both Clang and GCC. Your platform provider may decide to put on additional restrictions, but the compilers support mixing this without even a benign ODR violation, which is kind of nice. So how do you know if your compiler supports this mixing? Read the documentation. The expectation is you probably can, but we haven't upstreamed yet, so we don't know. But you still have to know about inlining and templates if you want guarantees of things happening in your translation unit. Item 5 is understand the limitations of this really version 1 of contracts. We don't get to put custom error messages in. You remember when we added static assert, and then in a later standard we added static assert where you could put comma, quote, error message? Useful, right? We added it later. We'll add it later here. The same idea. But you don't get that in the first iteration, which means that your automatic fingertip instinct to write ampersand, ampersand, quote, string, explanation string still works, same as assert, right? And string literal in your assertions, and you'll still get a reason, but we'd like to do better. We don't yet support them on virtual functions or pointers to function, and we don't have contract groups or labels right now. And those are things that are being actively worked on. We have per TU semantics today with the limitations of item 4 and a single global violation handler. So those are a few best practices. They're all the ones I know about right now, but we're learning this. But it's a fairly short list so far. Now, why are certain parts of the design as they are? Much has been made of the committee trying to make a minimum viable product. After we failed to get it into the contracts into C++20, the group tried very hard to decide, okay, what's minimal and viable? What's a thing we can build on that doesn't close any doors, but that's useful on its own? And so this slide is to go through the major features, and I will defend to you why I think they're pretty minimal. Not entirely, but pretty minimal, because these things are necessary. Let's start with pre and post. By the way, pre is the important one. Post is also nice, but I could have lived without post in C++26. Pre is the important one. Why? It is a major advance to put your assertions out of the body and glorify them up to the declaration where everybody can see them, including tools can see them. Yes, tools can go into bodies right now. It's so much easier on tools. If you just say your precondition in the declaration, rather than force them to go spelunking, force them to have a function body, and then do logic to figure out what you meant, what precondition you intended. It just makes it so much easier for tools. Oh, and contract assert is also better than a macro. Enough said. The semantics. Well, of course we need at least the first and third, ignore and enforce. I mean, even assert gives us that, right? But observe and quick enforce, and here I'm speaking from my own point of view as someone who I started looking at this in the last couple of months, not just because I heard the concerns and wanted to know for myself and take a deep dive for the first time and look for myself, but also because I'm now wanting to use these in production. And I have requirements to see, can this be something I can use at my company? And it is very important, a very important thing that assert has never given me, that I can turn checking on in production. Because I am not terminating in production, let me tell you. At least not at least for all my code. Some code maybe, not all code. So assert, sayonara in production. Like, it's a non-starter. But observe lets me enable checking in production, and which is also useful for testing new predicates. I add new contracts, but I'm not 100% sure yet, so I want to see if they fire first. Observe mode is great for that because it will check them and call the violation handler so I can see what fired in production. And then quick enforce enables enforcing in production with the absolute minimum impact on size and perf. And where do you want that, especially in security hardening applications? So again, I'm not saying the contracts are a security feature, but when, for example, the hardened standard library provides guarantees and implements them as an implementation detail, as contract asserts, it darn well wants fail fast in those security applications. In fact, quick enforce was, if I recall correctly, motivated by Apple for that reason. And the violation handler, finally, the fact that we even have one, oh, we need that so badly. Why? Because every single one of us has our logging framework, our error reporting framework, where we have a dashboard, we send it off to our CTO when bad things happen, and then they ream us out and we promise to do better. You know, all those things. We have our frameworks for this. All I need is a hook. Give me just a hook and I can call all that existing rich infrastructure I've got, and I can plug it into my dashboards, my monitoring, and I can send that, should I say this? Send that pager alert to somebody at 3 in the morning. Like, go fix your bug now, or maybe in the morning after breakfast. So to me, I see value in contracts in two directions. And again, here I'm just speaking from how I see it. I have not been told this by anybody else. This is just what I've intuited and the value I see for my uses. Shift left is huge. The earlier we find bugs, the cheaper they are to fix, right? It just always, every step earlier, an order of magnitude cheaper to fix. It is way easier to fix bugs at test time, if I can find them at test time, than in production, usually in front of my CTO's favorite customer, right? So shift left is a no-brainer. It's obviously good. But then I want to also run them in production, at least in observe mode, to enable to find things that went through, because maybe I didn't test every code path, maybe I didn't test every data possibility, and I still want to know as a safety net. That's not where I want to find them. I do not want to find them in production, but it's better than not finding them at all. And why is this viable? It doesn't close the doors to future evolution to things like custom error messages, virtual functions, function pointers, labels and groups. Let me give an example of one of those things. And thank you, Nina, for pointing this out to me. Nina is one of the implementers of the GCC implementation of contracts and our committee secretary. You'll see some of these same people, by the way, at the committee fireside chat panel this evening. One future extension example that we can add post C++26 is the idea of a no accept, enforce, or observe. So the idea is, what if we actually embraced throwing violation handlers, and then programs that did not want an exception but wanted to terminate could just say so with a semantic? That's what no accept enforce and no accept observe would be. And these are implemented in GCC, but they're extensions. They're not part of what's in C++26. And I want to quote Ville Voutilainen here, one of the EWG Evolution Chair Emeritus and a GCC hacker guy, that's an understatement, smart guy. And I want to read you exactly what he said about this way of dealing, of unifying, potentially throwing violation handlers, even for code that doesn't want to throw, by letting them opt out with a no accept, enforce, or observe. The breakthrough realization, the epiphany, and the stroke of genius. Ville is Finnish. He doesn't normally give glowing praise like this, all right? Like, this is not culturally correct. Like, he's very impressed. The breakthrough realization, the epiphany, and the stroke of genius there is that instead of trying to cater to two different crowds by making the violation handler no accept or not, we can serve two crowds with the same violation handler. If it throws, the authors of components that don't want exceptions to escape get what they want. The authors of components that want exceptions to escape get what they want. The different decisions can be mixed in the same binary, and one violation handler does what both audiences want. Author A compiles with no accept enforce, author B compiles with regular enforce. The same violation handler works for both, no linker magic. Remember what I said about novel magical linkers? No linker magic, no tricks, just different compilation of the violation handler calls. Done in the wrapper functions, meaning the implementation inside the compiler, the wrapper functions we already have. This is an example of the previous slide of this design has been thoughtfully put together to try to keep future extension doors open. So we talked about the rationale. Now let's talk about some frequently asked questions, including, I'm going to make so far in the talk, if I hadn't said the thing at the beginning, at this point, the folks who love contracts will think, hey, Herb's mostly on our side, and the others may be more grumpy. Just hold on for that when we get to the open questions part. So let's talk about frequently asked questions and open questions. Do C++26 contracts have lots of implementation-defined behavior? Yes. About 2 pages worth. There's a description in the papers about 2 pages worth. However, there are things that we usually do make implementation defined. There's some discussion about a couple of them, but basically some of them are compiler switches, and we just never tell in the standard what a compiler should do, what switches it should support, what build modes it should support. Those are things that are beyond the standard, and that's totally fine because that's the world we live in. We know the switches are different in different compilers. We know the groups of switches to use. They usually provide convenient defaults that are right for their platform. So you do want to give latitude to things at least like switches and build modes. Are C++26 contracts hard to implement? Now, I just mentioned this because over the past couple of years, sometimes I've heard, oh, certain detail pointing at a certain line in the proposal is super hard or impossible to implement. If so, they've been removed because we have 2, I'm told by the experts, including people who have looked at the code who weren't the authors, that we have in GCC and Clang 2 complete implementations with lots of extensions as well. So a superset of what's in the standard, not been upstreamed yet. When they'll be upstreamed, hopefully starting in the next couple of weeks, then we'll get more eyes on it and validate that. But so far, no, not hard to implement. One place where this came up is if you have 2 predicates in a row, there used to be a bug, and this used to be true, where one could elide the other. I think I've got a FAQ on that. But we fixed that. We put in an observable checkpoint, which is pretty much like an opaque function call. We already do this for opaque function calls. We don't know if it might have side effects. So we basically used very similar ideas there. It might require the compiler to do that check in a new place, which can require some updates, but it's not like a ground-shaking new feature. Is it true that C++26 contracts don't help static analysis? I happen to know a fair amount about static analysis, but I am not a static analysis expert, so I will refer you to the talk on Thursday by people who are, GitHub CodeQL and its experience with and expectations of being able to work with contracts. Now, there is one distinction that I can make. So is it true that C++ contracts don't help static analysis? The argument for no is, well, they do. They move the predicate out into the function declaration where you can see it, and that does make it easier for static analyzers. They put the expressions up where the analyzer can do less work to see them. That is strictly less work to do the analysis they already do. However, static analyzers do other things besides expressions. And some had hoped that contracts would let you express non-expression kinds of things too. These do not do that. So does C++26 contracts light up static analyzers? Yes and no. Yes for expressions. No for non-expressions, but that could be a future extension. But that's an important distinction. But see that talk to hear from people who actually know what they're talking about. Is there a portable default behavior? If I just write a line of code and put it in a book that says, hey, contract assert, can I reasonably expect that people who read the book on who knows what platform and compiler can try that out and get reasonable results, get results that I can tell them about? Very likely, yes. So the C++ standard says the recommendation is that implementations, that compilers default to enforce semantic, and that the default violation handler prints the source information and the predicate that failed, things like that. And that's in fact what GCC does. Here is a cut and paste of a current GCC message. I shortened the file name to save a couple of lines because it was a really long file name. But the rest is a cut and paste exactly as it was, which is pretty reasonable. So is there a portable default behavior? In practice, yes. Even if the standard doesn't deliberately require it, it certainly strongly recommends it, and the two current implementations are following suit. And this is the one I talked to already on the previous slide. Do contracts have a flaw where if I write undefined behavior in code protected by a contract, it can silently eliminate another contract check by time travel optimization? And I'm not going to explain the example because anything with time travel optimization is deep and weird. And especially because the answer is not anymore. That was a problem, but we fixed it, so thank you. And that's the observable checkpoint semantics that I referred to. So fortunately, we don't have to teach that, at least, so that's an improvement. What happens if you try to write pre or post on a virtual function or a pointer to function? Doesn't compile, not supported yet. I've seen that described as a pitfall. I'm not really sure why. In C++11, we had the arrow auto return type for lambdas, deduce return type for lambdas, but not for regular functions. If you tried to write it on a regular function, didn't compile. So there was a feature that worked on some functions, but not others. And then in 14, the feature was popular, so it was added to other functions. And we intend to support pre and post on virtuals as well. There is still some constipation about constification. There, I said it. This idea that in a predicate, things are implicitly const, which can affect overload resolution, right? Like it can make the predicate do something different than it would have if you wrote it in a contract assert than if you'd written it on the line before outside the contract assert, right? Absolutely true. That has freaked out some people, including it freaked out me. I'm feeling much better now. And the reason is twofold. The first reason is I remembered I already lived this nightmare, and it wasn't so bad. I lived this nightmare back in the 2000s when we were adding Lambda functions to C++OX. And people argued strongly that by value capture is const by default. How many of you have written a Lambda capture where you captured by value, tried to modify it, and scratched your head for 5 minutes trying to figure out why it didn't compile? And then you learned you have to write mutable on the Lambda. And you went on with your life. So did I. I still think it's a little quirk, but it's not so bad. This one is better justified. With the Lambda case, it was just, you might accidentally have a side effect, but it's my object. Get your fingers off my object. I know I captured it by value. I did that on purpose, right? Here, it's so easy to write an error. This actually has more value in the implicit const than with the Lambda capture. So anyway, we have prior art, and it really wasn't so bad. Hasn't really been a major problem. The other reason is because no one has yet, not despite lack of trying, has actually come up with any close to realistic problem example. And in the same talks where I see people give a non-realistic problem example, they have other examples where the Constification actually found a bug they wrote. So we have prior art that it finds real bugs, including by people who are trying to prove it useless. And we don't yet have a positive example where this is actually harmful. And we have prior art in the standard. So I feel better about it than I used to. But that's a year ago, asked me a year ago, I would have said I was more uncertain because I didn't know as much. This relates to why aren't C++26 contracts a drop-in replacement? I already have assertions in my code using my homegrown library, but I can't just replace my assert with contract assert. I've seen this mentioned as a pitfall, but all of the examples I've seen fall into two categories. The first category is, yeah, it's different, like the parameter order might be different, or it's because your library uses a macro and this is a language feature. A language feature is better than a macro and it just will be different in some ways than a macro. But usually in good ways that we want, right? And the second set of examples was Constification. They said, my assert of this thing always compiled. I changed that to contract assert and it wouldn't compile. Why? Because he wrote a side effect in his assert. So the fact that it didn't compile was a feature, not a bug. And that too made me feel better about Constification. But at least for once I got to say that people are constipated about Constification. Sometimes when things just fly off stream of consciousness, you don't think there's anything objectionable. And now I'm going back thinking, is there anything bad about that? I sure hope not. If it is, I apologize. I don't intend anything. Open questions. There are things we do not know. I started off by saying we do not have the implementation experience we wish we did. Contracts have not been used and deployed widely. I know a couple of companies have done that with prototypes. They have not been in shipping compilers, they have not, as non-standard extensions, they have not been deployed by multiple large companies in anger. So there's a lot we don't know. We think we're safe because of mitigations of lack of knowledge, but there are things we don't know. One of the things we don't know, right now, if you do, say, a precondition or a contract assert, and that predicate is true, nothing happens. If it's false, you terminate or call the violation handler, or whatever, you enforce it. If it doesn't tell you either true or false, but instead it throws, the current design says that is treated as if it had returned false. That a failure to even evaluate the predicate is a failure of the predicate. That turns out, we think, to be cheap to implement on Itanium ABIs, but again, more measurement is needed. So there's two questions about this. First, are those good semantics? Some say, hey, that sounds pretty good, and some are still worried about that. The second question is the runtime cost acceptable? And here is where you need to know a truth. The only way you can implement that is to essentially put a try-catch around the predicate evaluation. And then rely on being able to optimize that away, hence the hopeful conjecture. If most predicates are trivially no except, non-throwing, we can elide most of these checks. I'm going to call out Java think here, because that's how Java designers think. They say, well, let's have this overhead and hope we can optimize it. We'll probably be able to optimize that away. That's not how C++ normally does things. The way C++ does things is we have zero overhead by default, and you opt into overheads. This is not that. And that's why it should be a concern. Now, so we can maybe alleviate that concern with measurements. It might be okay. That doesn't mean it's damned to perdition, but it means it really does bear scrutiny. Also, it can be mitigated by a suggested extension of evaluation semantics that don't translate predicate exceptions into contract violations. So even if it is a problem, a future extension could also solve the problem and eliminate the overhead. Finally, on this slide, we can't yet write functions that don't exhibit undefined behavior when a precondition is violated. So there are suggestions to post C++26 add a label, for example, to be able to say, hey, I want this precondition always to be quick enforced, even if the rest of the contracts around me might be observed or quick enforced or something else. And the key to me here is, as far as I know, and again, I could be wrong, But as far as I know, these are compatible extensions that could be added on the foundation. And here's one more. Groups and labels that I just talked about. Clang has gone ahead, and here's a screenshot of some of the documentation, has actually given granular labels that have hierarchies where you can actually have groups of things, named groups of things, and they have custom switches for it. This is exactly an example of a benefit that if we ship contracts in the standard, that enables these experiments. Because we'll never get these experiments in experimental branches. We'll never get a production experience until a vendor in trunk ships an extension. Even if that extension is labeled experimental, now people can actually try it in real code. And it can get some adoption, and we can get more data. This is one of the reasons why having at least a minimum viable product to start with helps bootstrap, helps accelerate. So that covers the motivation, why defensive programming, the overview of what do we have, what are the best practices, why is each piece there, and some frequently asked questions, including open questions. But I'll go back to what I said before at the beginning. It is absolutely true that there are open questions and some serious concerns about the design. I think it is also true that it is unlikely that we could do significantly better than what we have, flaws and all, in a world where we have translation units and today's linkers, our current model, without, I don't want to dismiss it as wishful thinking, without hoping for future magical linker improvements that would take time to deploy. It's a tough problem, and the important problems are never easy, right? If it was easy, anybody could do it, and we would have had it in C++20. But thank you to everybody who's worked on it. Thank you also to the people who continue to critique this to make it the best it can be, and if we find a showstopper feature, a showstopper problem, we will deal with that. There's still 2 meetings left to review. But that is the current state as I understand it. Again, I am not one of the people who've been in the fray for the last 6 years, so any errors are my own, but thank you to everyone who answered my questions in email, including late at night on the weekend as I tried to put this talk together over the last couple of months, but when I tried to put this talk together in the last week or so. Thank you all, and I hope you enjoy the rest of the conference. Thank you for your time today.